If you're in sub-Saharan Africa, you know that mobile money isn't just a convenience. For many, it's a lifeline. We're talking about over 2 billion registered accounts. It's an incredible story of financial inclusion.
It is, but that success has created a massive shadow,
A dark side.
a huge one. When mobile wallets become the main way people bank, they also become a giant target for criminals.
Hmm.
We're seeing incredibly sophisticated financial crime sim swaps, identity fraud, you name it, and it's evolving fast.
And at the same time, institutions are getting squeezed by really tough data privacy laws, right? Things like Uganda's Data Protection and Privacy Act.
Exactly, which is heavily influenced by big global standards like GDPR. And that creates this enormous dilemma for the people trying to fight the fraud.
So spell that dilemma out for us. What's the core problem?
It's a classic big data paradox. To build good machine learning models, the kind that can actually spot these new fraud patterns, you need massive amounts of data.
Okay, that makes sense.
But the real mobile money data is, incredibly sensitive. You can't legally share it. And maybe the biggest problem for AI is that it's super imbalanced. Real fraud is, less than 0.5% of all transactions?
So your model just learns to ignore it.
It just learns to predict not fraud every time and gets a 99.5% accuracy score while being completely useless.
So you need the data to fight crime, but you can't use the data because it's private and skewed. That is the paradox we are diving into today. We're unpacking the work of Dinesh Azamuke from Maker University, who developed an approach to solve this exact problem.
It's called differentially private synthetic data generation.
It's a mouthful, but the mission here is to understand the mechanism. How do you create artificial, usable, and crucially legally compliant data that perfectly mimics the real world?
Right down to the fraudsters themselves, without ever compromising a single real person's privacy.
Okay, let's unpack this. I guess we have to start at the very beginning. How on earth do you build an entire artificial financial world from scratch?
So they used a technique called, it's called agent-based modeling, or ABM.
Yeah.
Yeah. And you should forget traditional stats that just look at, averages. With ABM, you simulate a whole complex system as a collection of individual actors or agents.
So they're all acting independently.
Independently, based on a set of rules. And when you have millions of these agents interacting, you get these complex emergent patterns that start to look just like the real world.
It sounds like SimCity, but for mobile finance. Who are the main players in this simulation?
That's a great way to put it. It's like a digital twin of the ecosystem. You have 4 key agent types. First, the everyday clients, the users.
Us.
Yep. Then the mobile money agents, who are the people on the street handling cash in and cash out. You have merchants accepting payments. And finally, the banks in the background reconciling all the funds.
And they're all performing a few key actions. Right.
5 main ones: deposit, withdrawal, transfer, payment, and debit.
And it's important to note, right, that deposits and withdrawals, that's most of the traffic, just the daily churn.
Exactly. They dominate by sheer count. But it's the transfers person-to-person payments that are often the really high-value ones.
And where the big-time fraud is probably hiding.
That's where it hides. And this is why ABM is so critical. It isn't just about making more data. It's about making balanced data.
You're solving that class imbalance problem you mentioned earlier.
Precisely. The researchers can now manually inject different kinds of fraud into their simulation. And they can crank up the rate, so instead of 0.5% fraud, they can generate a data set that's, say, 50% fraud.
Which is perfect for training an AI model.
It's exactly what the model needs to learn.
But wait a minute. If you're manually injecting fraud, aren't you just teaching the model what you think fraud looks like, not what it actually is? It sounds like you could really bias the whole thing.
That is a critical point. And it's why the calibration process was so rigorous. This synthetic world wasn't just built on imagination.
It's grounded in real data.
In 2 kinds of real data. They took quantitative stats from over 42,000 real transaction records. But, and this is key, they also grounded the model in qualitative insights.
What does that mean? What kind of insights?
It means interviews, focus groups.
Yeah.
They talked to 534 stakeholders across Eastern Africa.
Wow.
Yeah, not just customers, but the agents themselves, the merchants, even the regulators. This made sure the synthetic data didn't just match the statistics, but also captured the human nuance of how people behave and how criminals actually operate, according to the people on the front lines.
Okay, this is where it gets really fascinating for me. Once the platform was calibrated, they had to program the crime. So let's zoom in on what those 534 people told the researchers about how fraud actually happens in the real world.
They identified 8 main types. The most common, by a long shot, was account takeover, or ATO. That was 25% of all reported fraud.
A quarter of the entire problem. And that's your classic SIM swap attack, phishing, that kind of thing.
Exactly, just stealing credentials to get into an account. After that, at 20%, was split deposits.
Split deposits.
This is often collusion. An agent might tell a customer the system is down or their limit is low, then process a large cash deposit as two smaller ones, and just siphon off a piece for themselves. It's a subtle kind of internal corruption.
So the model has to replicate actual human deceit. That's amazing.
It does. Then you've got fake credentials at 17%, which is opening accounts with forged IDs, and SIM upgrade claims at 15%.
Which is more of a social engineering trick.
Yeah, tricking people into participating in a fake network upgrade that gives the fraudster access.
So the real engineering challenge is translating these messy human criminal schemes, collusion, lying, forgery, into structured code that these artificial agents can actually execute. How do you digitize a scam?
They use a structured parameter file, a .graph mel file, which is basically a script for a crime,
A recipe for
a
fraud.
recipe for fraud. For each type, it defines three things. First, the node classes, like a compromised account or a mule account for laundering. Second, the edge actions, which are the steps, like a takeover command or a cash-out move.
And the third.
Most importantly, the amount profiles. These are probability distributions that define the typical transaction size for each step of that specific criminal scheme.
So the crime's actual signature, the timing, the sequence, the amounts, is literally coded into that file. That is just phenomenal. But okay, that's the utility half. We've got good, accurate data. Now for compliance, how do you make it legally safe?
The answer is differential privacy, or DP. And we really need to stress how big a leap this is from older, weaker methods.
Like what? What did people used to do?
Things like k-anonymity or just data masking, where you swap or hide names and IDs.
And those don't work, right? Why is adding statistical noise better than just hiding an ID?
Because masking is so vulnerable to what are called linkage attacks. An attacker can take your anonymized data, combine it with some other public data set like voter records, and mathematically re-identify people. The mask breaks.
And DP prevents that.
It prevents it entirely because it offers a formal, mathematical, quantifiable guarantee that is statistically provable.
So the guarantee is the difference. The core idea of DP is that if you remove my specific transaction records from the original dataset, the final synthetic output will be statistically identical. My presence or absence has no effect.
That's the core concept. It mathematically severs the link between any one person and the final data. Now, the big innovation here is how they applied it. They didn't just generate the data and then, sprinkle some noise on top at the end.
They built it in from the very beginning, at the generative stage.
Precisely. The model uses what's called the Gaussian mechanism to inject a tiny controlled amount of noise when it's computing the aggregate inputs from the real data.
So things like the total number of deposits in a month or the average transfer amount, those big picture numbers that guide the simulation.
Yes. Let me try an analogy. Instead of giving me a list of millions of private transactions, you're only giving me the overall recipe for the ecosystem.
Okay.
But you've put a tiny, controlled, mathematically safe amount of, say, sugar in that recipe, so I can never reverse engineer whose specific flour was used to make it.
That's a great analogy. That's spot on. By adding noise to the recipe itself, you guarantee that my individual ingredients have a negligible impact on the final cake.
That's it. It is privacy by design.
All right, this is the moment of truth. You've solved the privacy problem, but does adding all that noise ruin the data's usefulness? You can't fight fraud if your models are trained on junk. We need to see the proof.
They ran 3 major validation tests. First, to check statistical closeness. Does the synthetic data have the same shape as the real data? They used the Kolmogorov-Smirnov test, or KS test. The results were conclusive. Both the regular synthetic data and the private DP-enhanced data were highly similar to the real stuff. The p-values were high, well above the threshold, which confirms the distributions weren't distorted.
So the shape is right. What about systemic bias? Did the noise push all the numbers up or down?
That's where the Bland-Altman analysis comes in. It specifically looks for that. And again, it showed minimal systematic bias and really strong agreement. Over 92% of the data points fell within the statistical limits of agreement. It proves the synthetic data reflects the right scale and frequency.
Okay, so it looks right, it feels right. But the final test, can you train a model on it that actually catches fraudsters?
That's the bottom line. And yes, They tested key classifiers like random forest and XGBoost, and they got high predictive performance. We're talking AUCs of at least 0.79, even with the privacy constraints.
An AUC of 0.79. For anyone who's a bit rusty, what does that mean in the real world?
It means the model is very good at telling the difference between a legit transaction and a fraudulent one. A score of zero point 0.5 is a random guess, so 0.79 is considered strong performance. But what's really amazing is the inference fidelity.
What's that?
XGBoost, in particular, showed 95% alignment and feature importance with models trained on the real private data.
Meaning the noise didn't stop the model from learning to look for the right clues.
The right signals. It learned to spot the same fraud indicators. The utility was preserved.
Utility confirmed, but let's go back to the privacy promise. We need to know for sure. Did the noise actually work? Did it protect the individuals?
To check, they ran the gold standard audit, a membership inference attack, or MIA.
An MIA, so that's basically an attempt to hack it.
It simulates an attacker who's trying to figure out if your specific data was used to train the model, and the results were decisive. The DP mechanism worked beautifully.
Give us the hard numbers on that.
The attacker's chance of success, their AUC score for guessing right, dropped from 0.79 on non-private data all the way down to 0.59 on the private data.
Wow, that's a huge drop. That's almost down to a coin flip.
It's almost random chance. And more than that, the ability to identify a true member with 0 false positives, a high confidence attack, fell from 14% down to just 3%.
Okay, 3% is a massive reduction, but it's not zero. Is that small residual risk just the trade-off you have to accept?
It is. It's inherent in that utility privacy balance. To get that 3% even lower, you'd have to add so much noise that the model's performance, that 0.79 AUC, would start to suffer. So the researchers found what they felt was the optimal balance point. Protection worked and utility was preserved.
That's a powerful conclusion for regulators. Let's talk about the final piece of the puzzle. A tool called MomMT Lab.
Right, the Mobile Money Transaction Laboratory. This is a visual analytics platform they built on top of the data.
And this turns all those numbers into something an investigator can actually see and interact with.
Exactly. Transaction data is a network. So a graph database like Neo4j is perfect. It models everything visually. Nodes are the people, the merchants, the IDs. Edges are the transactions connecting them. It lets a non-expert visually explore these incredibly complex flows of money.
So give us that visual aha moment. What did they find when they looked at the graph?
Well, they ran a query using the cipher language, and they were specifically hunting for one pattern: clusters of shared PII.
Shared personal identifiable information.
Exactly. They searched for phone numbers or national identification numbers that were connected to multiple different client nodes, and boom, the platform lit up. It visually revealed these clusters of identity theft and collusion. You could literally see multiple clients all being controlled by the same underlying identity.
Which is exactly what the stakeholders told them about in the beginning, the fake credentials schemes.
Precisely. It was the final validation. It proved the model was replicating the real structural fraud patterns that exist in the ecosystem.
So let's sum this up. The MomMT SIMDP model successfully navigates that trade-off between privacy and utility. It creates synthetic data that is sound, compliant, and highly effective for training fraud detectors.
And that's not just academic. This gives financial institutions and regulators a real, practical tool, a shareable, privacy-preserving sandbox.
So they can test new fraud controls, new policies, without ever touching real customer data.
Exactly. It creates a secure way for the entire industry to collaborate on fighting crime without violating data laws.
Which leads to a final, bigger question. The study mentioned limitations, of course, like fine-tuning those privacy parameters, and the fact that fraud is always evolving. Looking forward, what's the next frontier for this kind of work?
There are a couple of really exciting directions. One is integrating things like large language models, LLMs, to make the agent behavior even more realistically human. But I think the most fundamental next step is developing federated or decentralized DP mechanisms.
Meaning?
Imagine different banks or mobile operators all collaborating to train one giant, super smart fraud model. But they do it without ever pooling their raw data in one place. Each one keeps their data safe, but they contribute to a shared intelligence.
That would be a game changer.
It would. And it leaves you with this really provocative thought. How might that kind of decentralized data synthesis fundamentally reshape not just fraud detection, but global financial data governance as a whole? That's the next great challenge.